this video we're going to be looking at measuring the spread for continuous random variables. So if we look at the graph down at the bottom here, we've got a long flat yellow distribution where the data values are spread out over a large area. They're concentrated over a larger area. And we can compare that to the green function and the blue function, where the blue function, most of the data is really close together here with only little bits off to the side that are quite infrequent. And so we're going to look at ways to measure and compare how spread out the data is. So we're going to do that, and we're going to look at different measures of spread. We're going to look at the variance and the standard deviation. And we're going to start to look at percentiles, quartiles, and then tie those into the interquartile range. And then finally look at the range of the data. You'll be interested in percentiles because that's what the ATAR is, a percentile. Let's look at the variance. So the formula for variance that we use with continuous random variables, we use the little sigma squared, we use variance of x, is exactly the same formula that we use for discrete random variables. We haven't really used mu very much here with the formula for variance, but it is, if we look down here, it is exactly the same as the formula that we were using for discrete random variables. We just need to tweak these to fit our continuous random variable. So we'll be using integrals for these. So on the formula sheet that you get with both of your exams, this is the formula for variance that you'll see for continuous random variables. And it has this pattern in here. So it fits this E of x minus mu thing. What it actually means you need to do is you need to work out what your mean is, and then you can substitute your mean value in here and then use this formula here. The other way that you can do it is to use this setup for the variance, this variety of the variance formula, and just use this formula here, which is often easier to use on your CAS because you can copy and paste your mean from up above. So this is the one that I would be suggesting that you use, and I would be suggesting that you work out your mean here. So this is your mean. Most questions will ask you to find the mean first, so you would work that out on your CAS calculator, and then you can just copy and paste it down. So let's have a look at an example of a question for the variance. So I've left the formula we're going to use up the top here. A probability density function is defined by, here's our function here, and so the area that we're working with, the section that we're working with that gives us area under the curve, is this section here. So for our integrals, our endpoints are going to be based around the endpoints for the domain for the part of the function that contains area underneath it. So let's go ahead and fill in our formula. So we are integrating, first of all, x squared times the function, so x squared times the function from our limits from 0 to 3, so 0 to 3 here. And then we take away, and be really careful with this, square brackets around the whole of the integral for the mean, and square on the outside. This is where people make mistakes, getting this bit here wrong. If you're going to be doing this on your CAS calculator, make sure as you come out of one integral that you're getting the really long cursor flashing at the end of the dx before you move in to try and put the minus sign and then the next bit there as well. So then all we do is pop that into our calculator, and you can see that I've done that there. See, I've got very big brackets here for the integral with the squared. And that's it, pretty much. That's how you work out your variance. So our work with variance doesn't give us any kind of real information about the function itself and how spread out it is. We actually need to take that next step and find the standard deviation by square rooting the variance. And what that actually gives us is the average of the distance of each data point from the mean of the distribution. So over here I've got a bit of a distribution that I've just made up, and there's your mean. And what the standard deviation does is actually works out for this distance plus this distance plus this distance, this distance, this distance, and this distance, what the average of all of those distances are, so that we get an idea of how spaced out the data is. Now, one of the uses of the standard deviation, not only in telling you how spread out the data is helps you to find there are certain patterns to how data generally fits in relation to the position of the mean and the standard deviation. And that is that 95% of all data points for a distribution are generally within 2 standard deviations of the mean. What that means is that 95% of the data captured in this little section here, this is 95% of the data, that's captured between the mean and 2 standard deviations out, so 1 step, 2 step out, this value here, and 2 standard deviations in the other direction, this value here. So the sorts of questions you get around this idea are things like, for the number of minutes for a takeaway delivery, it's a continuous random variable with a mean of 45 and a standard deviation of 10. And what they're asking us to do is find the approximate time interval for a delivery of time for 95% of all takeaway deliveries. So between how many minutes on average do the 95% of the takeaway deliveries occur? So what we do is we use this probability definition here, that the probability that something lies within 2 standard deviations of the mean, that's how we say that, within 2 standard deviations of the mean, is 0.95. So how do we go about working out those values? So what we do is we take the mean value of 45 for here. Let me just put that on the top. So that's 45, that's 45. We have our standard deviation of 10 minutes, so we put 10 here and 10 here. And then we can work out what those values are. So we've got we've got 45 there and there, one's minus, one's plus, 10 and 10, and then we can simplify that down to say that 45 minus 10 gives us 35 minutes. Oops, 35 minutes, that should say 20, and that should say 20 because it's 2 lots of it. So that gives us 25 minutes and 65 minutes. So we expect 95% of deliveries, takeaway deliveries, to be completed between 25 and 65 minutes. Our next measure of spread is percentiles, and percentiles are the x value. So they're not an area, they are the value of x that has an upper bound, that is the upper bound for a particular area under the probability curve. So I've got just a flat probability density function here because it makes it easier to see. So if this is our lower bound and this section here contains 40% of our data, or an area of 0.4, whatever this x value here is the 40th percentile. So this is 40% of the data. This is 40%, that area. And so whatever that x value is there, that value is the 40th percentile. It's the same for our next one across, our blue one. That area there is 20% of the whole of the area under the curve. So whatever that x value is there is the 20th percentile. We've got the 75th percentile here and the 99.95th percentile. Does that sound familiar? 99.95? Well, this is literally where they get your ATAR score from. So your ATAR score of 99.95 means that 99.95 of the x values, so this is the x value here, 99.95% of all the other x values are lower than you. So if your ATAR is 50, you are in the 50th percentile, so 50% of the students are below you. The ATAR is a percentile, and that's why you can't get an ATAR of 100, because they only measure the step-ups in 0.05s of a percentile. The next statistics that we use to measure spread are quartiles, and quartiles are just special percentiles basically. So the 25th percentile we call quartile 1 because it has 25% of the data below it, so a quarter of the data is below quartile 1. The 50th percentile we refer to as quartile 2, so Q2 for short, and it has 50% of the data below it, and it's also known as the median, so it has two names. And finally we have the third quartile, quartile 3, which is the 75th percentile, so 75% of the data is contained below this particular x value, and so that's quartile 3. And what we use the quartiles for is we use the quartiles to measure where is the middle 50% of the data, between which two x values does 50% of the data sit, and that we refer to as the interquartile range. And so the interquartile range is the difference between quartile 1 and quartile 3. So you work it out using the formula quartile 3 minus quartile 1. So let's have a go at doing that. So I'll leave the definition of the interquartile range up here at the top. Let's look at a question. Find the interquartile range for the function f of x is equal to 2x when x is between 0 and 1, and it should also say 0 elsewhere to make it a probability density curve. So what we need to do to find the interquartile range, we need the value for quartile 3 and the value for quartile 1. So we set those two up as probability questions where we're looking for the value of x. We've called the lower quartile A. That gives us 25% of the data, and the upper quartile I've called B, which gives us 75% of the data. And so I integrate the function from the lowest end of the domain over which it's defined to the letter value that I want. So here I'm going for A for 25%, so I've got A here, and here I've got B to give me 75%. when I do that integration using my CAS, then I get A is equal to 0.5 and B is equal to 0.86. So when I'm using my CAS, I'm solving this equation for A. And remember, when you do the solve function on your CAS, that the A value that you're looking for has to fit within these values here. So you can use the solve command and have it solve, comma A. Let me just write this on here. So you can do solve that for B, close brackets, given that, and then use the domain that you've got up here, but put your B in it. And then that way it's going to give you the correct value for B, because sometimes it'll spit values out that fit this integral, that will solve this integral, but it'll solve it outside of the domain because the calculator is just reading this as a whole function. It doesn't realise that there is some limit on what the value of B is. So don't forget to use that. And then finally, so we've got a quartile 1 value, we've got a quartile 3 value, and so then we just do our interquartile range as being Q3 minus Q1 for 0.36. So the final measure of spread I want to look at is the range, and so it's the difference between the minimum value for x, minimum value for x, so this x value here, and the maximum value for x, so this x value here. So this is our range. Seems fairly simple, but the reality is this is something that trips lots of students up. So let's have a look at an example. Here's a function. Let me just move this up here so we can see. Get that out the way. Okay, so this is where people have difficulties. So we've got a function defined from 0 to 3, so here's that function there. So normally what happens is you'll see a graph of the function for f of x, and immediately you'll go back to your definition of the range as being the range of f of x, which is this height here. Now you can see that what I've got up here, back up here up the top for my probability density function, is that the range of the probability density function is the range of x values. So this is the range of x values. It's not the range of f of x. And so that's the bit that trips people up. What you're actually after when you ask about the range for a probability density function is you're after the range for the random variable x, not the range of f of x. So just watch out for that one. That's a tricky one.